world problems. So we created some core areas in our school related to high performance computing, big data, analytics and visualization, machine learning, cybersecurity, numeric methods, real-world algorithms. And we put this together because we thought this is really what's needed to tackle some grand challenge problems on the horizon. Today, after about a dozen years as a startup within academia, our school is doing really, really well. In US dollars, we're extremely research active and have many leading projects in the United States and working with collaborators around the world. One of which is the National Science Foundation in the US has 4 big data hubs, and we are running one of those for the south part of the US. We have about 47 faculty and staff, and roughly about 260 or so graduate students in our department, and many of the faculty are award-winning leaders. So as I mentioned, the core research areas that we formed are really the types of areas that are closely related to this conference on machine learning and data sciences, ranging from high-performance computing, and I'm very impressed that the NVIDIA DGX-1 is here at Bennett University. That's a fantastic opportunity to understand how to co-design algorithms with special purpose devices, hardware, chips, etc. And I think that's going to be game-changing. We also look at involving that with application areas, machine learning, analytics, cybersecurity, and many other problems in computational science and engineering, everything from modeling populations to understanding climate, understanding energy efficiency, electronic medical records, health informatics. All of these areas require the designer, the programmer, the engineer, the scientist who can combine computer science, machine learning, mathematics, applied statistics, along with application and disciplines. We have had a number of strategic partners, and I was very interested to see also that Bennett is working with NVIDIA, working with Accenture, among other companies, as we have at Georgia Tech. And we have a number of new partners this year in my school where we collaborate very closely with these sorts of companies, including national laboratories in the US. And I think that's really important as you go forward with Bennett University to figure out your strategic partners in industry and in government, because the innovations will come from these partnerships that really spread across universities, industry, and government to make the world that we want to see in 5 years out, 10 years out in our future. We also are building a new facility at Georgia Tech called the Coda Building, and my school will be the beating heart, really the core of this new building that is an interesting way to combine a university and industry in a facility along with a data center to solve some of these grand challenge problems. That should open in about a year's time in Georgia Tech. Any of you who wish to visit Atlanta, let me know. I'll welcome you there, and you can help visit this inaugural building. So with that said, moving towards research, one of my own passions has been looking at data science and trying to use data science techniques to solve real-world challenges. And often we're faced with having very massive data sets, and we want to solve problems from financial, fintech, to understand communication networks, healthcare, a lot of real-world problems where we have different types of information coming from different sources, and we have very large volumes and different types of information. And what we would like to do is either make better decisions, find patterns within that data. And I think this is a very interesting time to be a computer scientist, because we now have technologies and systems and storage for massive quantities of data, many different types of sensors out there, and now a very rich algorithm and analytic space to reason about that information.
And after that, you will be in 3D and there will be a plane that you have to build with your identity.
I can even with me also.
Yeah.
It
Is it tight enough? Use your playing option. Keep gazing at it.
Finding community structures within large social networks, defending against nation-scale cyber attacks and also giving attribution to those attacks, looking for insider threats within organizations, improving the resilience of the electric power grid, detecting and preventing disease in human populations, and others. The hallmark of these problems is often that we are looking for rare events or single events, maybe interactions with single edges when you have trillions of entities within these types of networks. So these are really a grand challenge, and we've tried to develop techniques, algorithms, and data structures for doing near real-time processing of these massive graphs. Many computers that we have today, many supercomputers, really work well on problems that are regular, where our data structures, we can walk through the information in rows and columns like matrices. Yet the hallmark of many of the types of problems I highlight here are that they're much more irregular in nature. We may visit a vertex and then look at who is adjacent to that vertex, and often we are moving all around the computer system, and the running time becomes very poor as we're dependent on the memory latency. And we also do not know how to use all of those fascinating computer architecture techniques from superscalar execution, prefetching, deep memory hierarchies and caches that help the regular applications, but often hinder the performance of these applications. So I want to tell you a little bit more about what we've done in this area, and also a number of the projects that we've had to improve computer architecture and hardware-software co-design for these data science applications. One project that we lead is from the US Department of Defense Advanced Research Project Agency, or DARPA, where we are working in the program Hierarchical Identify, Verify, and Exploit, or HIVE. This program just launched this year, and it's quite exciting in that Intel and Qualcomm, two chip manufacturers, are making a new processor design that is going to be focused on graph analytics. We, over many years, have developed graph algorithms, software, analytic tools, and designed real-world applications based on graphs, but we've always been having to make do with the processors at hand that are good for many things, but often not fully designed for graphs. So this is the first time ever that we will see a processor that's purpose-built in software co-design for these types of applications. So this is a growing trend to look at graph algorithms, and we are coming up with what looks like a interface. What are the right kernels, what are the right primitives to design a processor where we also can have basic graph primitives as part of the instruction set architecture. So we are about not quite a year into this program, and we're really excited because this is a shift in this niche area of graph processing, but we see with commercial applications that there may be a trend for this to go mainstream, and we will get to influence that hardware architecture and create something that's purpose-built for graphs. That's exciting because it's sort of once in a generation that you ever get to influence a architectural design. Often we get driven by the processors at hand, and today's processors are primarily driven by the gaming and entertainment market, not by scientific and technical